Here's a tip. If you understand that a function is increasing where its derivative is positive, and it's decreasing where its derivative is negative, and if you can understand that a function is concave up where its derivative is increasing, and concave down where its derivative is decreasing, then all you should need to understand with concavity should be these notes. And I really hope that this is working out for you, because the alternative is to listen to me ramble in this video literally for 25 minutes. In the last video we talked about how to tell where a function is increasing and decreasing based on its first derivative, and this video seeks to go into a little bit more detail about the shapes of the curves when they're increasing or decreasing. For example, if you're told that a function is increasing because its derivative is positive, you can't really tell too much about the shape of that function just by the fact that it's increasing. Increasing could mean something like this. It could mean shaped like that, or increasing could be just a straight line, or increasing could mean increasing like this. So in each of these three cases, each of these functions is increasing, so the derivatives are positive, but they both have subtly different shapes, and we're here to determine how to tell which of these cases it's going to be. Most functions can be partitioned into four basic shapes. Those are, so functions could, generally speaking, they could look like, if they're increasing, they could either look like, they could be shaped like that, or they could be shaped like that. And if they're decreasing, they could be shaped either like this or like this. Most functions that you find can be partitioned into regions where they'll always look like this, 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 or this. Now, the words that we have to describe what these shapes are, we use the word concavity to describe it. This is concave up. We say that this shape is a concave up shape, and we say this is also concave up. This we call concave down, and this is called concave down. The functions don't always have to be exactly like this. They can be sometimes concave up and sometimes concave down. For example, if I draw something like this, say, we would say that the function is concave up in this region, and concave down in this region, and concave up in this region. So, just like I had here, the four shapes, we could partition this curve into a section that is concave down, and that ends about right here. Alright, so it would be concave down for this region, and then concave up thereafter. And this is true no matter how complicated I make it. If I make a more, let's see, if I have a really curvy design here, say. Alright, again, this function can be partitioned into regions that are concave up and concave down. So this is concave up until what looks like about right here, and then it's concave down, concave down, concave down, and then look, it turns up again right about here. So it's concave up, 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 and then it looks like it bends down again, and then so down, 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 and then concave up again. See that, right? So we have up, down, up again. So, question is, what makes the function have these sorts of shapes? Have these shapes? What makes a function concave up, and what makes it concave down? Well, just as in the last example, in the last video, it was all about the first derivative. So it's all about the first derivative here too. What I'm going to do is here. Let me just list these shapes again. So we'll have up. And let me change up the order a bit. I'll have up, up, and down, down. Alright, so concave up, concave up, concave down, concave down. What's this all about? It's all about what's happening with the first derivative. Alright, if the function is shaped like this, its derivative is increasing. And that's what it means, increasing. Same thing here, right? The derivative is increasing because the slopes are positive, say down here, and they're getting more positive as x gets bigger. Right? The slopes are increasing. And the same thing is true here. It looks a little bit deceptive because the function itself is decreasing, but if you draw slopes towards like it's really steep there and it's getting less steep, but the values of the slopes are increasing. It's more negative here and it's getting less negative. So something that's getting less negative is increasing. So if a function's derivative is increasing, it's going to have either one of these shapes. The other side to that is decreasing. In this case, the derivative f prime is decreasing because the slopes drawn here, all right, this one's a little bit easier to see. The slopes here are negative and they're getting more negative as we go to the right. And so f prime must be decreasing because f prime gives you the slopes. And in this case, f prime is, even though the function itself is increasing, its derivative starts out big and is getting smaller. It's getting less steep. The derivative is getting less. So the f prime is on the decrease for these two graphs. So in a nutshell, that's what determines concavity. We could state as a rule, if I'll say f prime is increasing, that implies that f is concave up. Concave up. And of course, if f prime is decreasing, that implies that f is concave down. That's all that you really need to understand what causes these shapes to be. How we determine concavity in practice, it depends on the information that we are given. The bad news is that you're not always given a graph of f prime to determine the concavity of f. In the case where you're not given a graph of f prime directly, but you still want to determine the concavity of f, you can always there's a way to figure out whether f prime is increasing or decreasing. We can tell where a function is increasing or decreasing by examining its derivative. So suppose that you're not given this graph here. All right, so you can't tell directly from looking at, you can't tell whether f prime is increasing or decreasing. What you could do is you will be able to examine f prime prime and make a decision based off of that, because you know that where a function is decreasing, its derivative must be negative, and where a function is increasing, its derivative must be positive. So if you can get this information, that's all that you will really need. For example, via the second derivative, you know if f prime is this, then its derivative must be negative here, must be positive here, and must be negative here, because the original function is decreasing, increasing, and decreasing again. From this sign chart, you can draw conclusions about the behavior of f prime and hence the behavior of f. So this is a pretty common test to determine the concavity of a function f when you're not given the graph of f prime. It goes like this. If f prime prime is less than 0, that means that f prime is decreasing. And f prime decreasing was our definition of f being concave down. And the flip side to that is if f prime prime is greater than 0, if f prime prime is positive, that implies that the first derivative, f prime, is increasing, which was our definition of f being concave up. And this is typically the method that we're going to use when we're confronted with problems. If you're just given an f of x equals whatever, typically what you do is you'll have to take two derivatives And to tell whether f prime is increasing or decreasing, you have to look at the sign chart for f prime prime. So if you were just given a sign chart, if you arrive at a sign chart for some function y prime prime, and you come up with something like this, say at a, b, and c, these are values of x, and suppose it's 0 there, 0 there, 0 there, and we get positive, negative, positive, positive, you can infer where y is concave up and where y is concave down. Because if y prime prime is positive, that implies that y prime is increasing, and hence y must be concave up somehow. Now, whether it's increasing or decreasing, that depends on the sign of y prime. But we're just going to examine concavity for now. Maybe I shouldn't even draw that. I should just say concave up. And since y prime prime is negative here, that implies that y prime is decreasing, and hence y is concave down here. And similarly for these two, right, since y prime prime is positive in both of these regions, that implies that y prime is increasing, and that implies that y is concave up in both of these. So let's do another example here. If you're given, suppose you're given the graph of y prime prime. I'll just draw that again. So we put the axis here. So here is f prime prime for some function. Draw the y-axis. I could say, where is f concave up? Where is f concave down? All that you have to look for, all that matters is the sign of f prime prime. I'll make a little chart. I'll make another chart down here that gives the correspondence with f prime. Right? So from here to here in this range, f prime prime is, it's decreasing, but that doesn't matter. It's all that matters is that it's positive. So since f prime prime is positive here, that means that f prime must be increasing in this range here. From here to here, f prime prime is negative, which implies that f prime is decreasing. And all throughout here, like, it goes up and down some, but it doesn't matter. All that matters is the sign. F prime prime is positive, which implies that f prime is increasing. And from this we could determine that the original function f must be concave up, concave down, and concave up again, to varying degrees depending on how how extreme this is, but it definitely is concave up, down, and up again here. So what's going on at these 2 points here? On the original graph, since since f prime prime is 0 here, and f prime prime is 0 there, since f prime changes sign at these 2 points, that means that f prime switches from increasing to decreasing, or vice versa, which means that f has inflection points here and here. That's actually what an inflection point is. An inflection point is where, so let me just write that out, inflection point. That is defined as where f prime switches from increasing to decreasing, or from decreasing to increasing. All right, that's the definition of an inflection point. Again, if you're not given directly a graph of f prime, if you can't just read it off a graph like so, there's a way that you can check it, because wherever f prime switches from increasing to decreasing, that means that f prime prime switches from positive to negative, or vice versa, right? So sign changes in f prime means that f prime switches from increasing to decreasing, or decreasing to increasing, which implies back on f that it switches from concave up to concave down. So it depends on the information that you are given, and you can be given a variety of data from which to draw these conclusions. Let me just go through a couple of examples, again given some varying pieces of information. If you're given a graph of f prime and you want to know the concavity of f, let's say it's shaped like this. All that matters is whether f prime is increasing or decreasing. So you would say that, I'll say, we can put all that you just look and see it's decreasing up until here, so that's going to be one spot, and then it's increasing from here to here, so that's another thing, and then it's decreasing from there to there, and then it's increasing thereafter. So what you can infer from this is that f, the function f, must be concave down, right? F is decreasing means concave down. F is increasing, f prime is increasing, that means f must be concave up. From here to here, f prime is decreasing, so that's concave down. And from here to here, f prime is increasing, so f is concave up. And we have inflection points. Right? We have inflection points for this x value, and this x value. And that's all that you need. If you're given a graph of f prime prime, you're going to look for different things. Draw it out again. Put it right here. So back down there. If this is f prime prime, now to determine the concavity of f, we're concerned about the sign of this only, just the sign. So I'll make another chart for f here. So the question is, where does f prime prime switch sign? Here it switches sign, so I mark that down. Here it switches sign, so I mark that down. And that's it. Even though it's 0 here, there's no sign change, so that doesn't change the concavity. But here, f prime prime is positive. That means that f prime is increasing, and hence f is concave up here. Here, f prime prime is negative, which means that f prime is decreasing, and hence f is concave down. And then for the remainder, f prime prime is, well, from here to here, it's still positive, so f is concave up. And then from here on, it's also still concave up. So that's it. To to determine the concavity using a graph of f prime prime, you just look for the signs, positive and negative, right? We got positive, negative, positive, positive. And how to spot the inflection points? The inflection points are going to be wherever this changes sign. So we're going to have inflection points here and here, but not here. Even though it's 0, it doesn't change sign, and that's all that matters. So here it's all about sign changes. In this case, it's all about increasing and decreasing, and you can find the inflection points by looking at the maxes and mins. So the more typical problems come when you're given actual functions to deal with. Let's see. I have two right here. Alright, so here's the problem. I have the derivatives worked out because I didn't feel like taking up video time doing it, but you start out here and it'll say where is y increasing, where is it decreasing, where is it concave up, where is it concave down, and locate all the inflection points. Since this video is on concavity, we'll go for the concavity first. You take two derivatives. Since you're not given the graph of y prime, you can't directly tell where this is increasing or decreasing, so you have to look at this. So just draw out a sign chart for y prime prime. Where is it 0? So it's 0 at 0, 0 at 0, and at 2 it's 0. If we plug in a number larger than 2, the second derivative will be positive. When we cross over 2, by plugging it in, we'll get negative, and then we'll get positive back over here again. So that means that the original function y must be concave up, then concave down, then concave up again. That's all that you need to do for concavity. If, as a bonus, you want to figure out where it's increasing and decreasing, you look at the sign chart for y prime. So where is this 0? This is 0 at 3, it's 0, and it's 0 at 0. So 0 at 0. And if I plug in the surrounding values, greater than 3, it'll be positive. Between 0 and 3, it'll be negative. Test them out. And less than 0, it'll be negative also, which means that the original function is decreasing, decreasing, and then increasing, all the while being concave up, concave down, concave up. If you put this into your calculator, you'll see that the graph should look something like this. The actual graph of f. You can see that. Here are the axes. Axis goes up here. So you can see how there's the correspondence here, right? Up until 0, it's decreasing and concave up. That's this shape. Why don't I fill this in now? And from 0 to 2, it's decreasing concave down. So that should be this shape. And then between 2 and 3, it's still decreasing but concave up. So that's that shape. And then past 3, it's increasing and concave up. So it's going to be shaped like that. And that sort of plays out here, right? It has that first shape here, and then the second thing to the inflection point, which occurs at 2. So that looks like it's about drawn right there on the graph. And then from there, and then, no wait, yeah. And then it's, right, concave up, concave down, concave up again forever. And decreasing up until 0, more decrease up until 3, so this must be the 3 here, right? Decreasing here, and then after 3 it's increasing again. So this is what that one looks like, and that's one example. The other example I have is a rational function. So once again, we're going for the concavity, so we could just, since we have no way of telling where this is increasing or decreasing as is, we go straight to the second derivative. And you plot the zeros and plot the points to make it undefined. If you set the top equal to 0, you get plus and minus radical 1/3. And it's 0 there, and it's 0 there. If I plug in a number greater than radical 1/3, the whole expression will be negative. If I plug in a number between, I'll get positive. If I plug in a number here, I'll get negative again. And that tells us that the function must be concave down, then concave up, then concave down again. So it's got 2 inflection points at plus and minus 1 over radical 3. If we're interested in more details, where is it increasing, where is it decreasing, you do another sign chart for y prime. That's 0 at 0, and that's the only 0. You plug in a number greater than 0, the whole thing is positive. You plug in a number less than 0, the whole thing is negative. And so f must be decreasing and then increasing, all the while being concave down, up, down. And if you plot this function, you will see, if I could sketch it up, it does look something like this. Let me see if I can get that up there. Something like that. So it's got inflection points here and here. Those are about right here and right here, even though I don't have them drawn the best. It's if I go to map this out, right, up until this point here, it's decreasing concave down. So that's that shape, which matches up with this. Between here and here, right, between these 2 points here, it's still decreasing but concave up. That's this shape again. Between these two, right, from here and here, it's increasing and concave up, so that's this, roughly speaking. And then after that, it's still increasing forever, but concave down. And you can see that's borne out in the graph, right? It's got the 4 shapes right there, decreasing all the while, increasing thereafter, concave down, concave up, concave down again. So just to recap what was done here, to determine the concavity of a function, it's really all about f prime. Okay, It's all about f prime. If f prime is decreasing, f is concave down. If f prime is increasing, f is concave up. Since we're not always provided with that information directly, what we have to do often is we go to the second derivative. And if the second derivative is negative, that implies that f prime is decreasing. Hence, f is concave down. And if the second derivative is positive, that implies f prime is increasing, which means that f is concave up.